Our last speaker in this session is Trisha Lian. She's a PhD student at Stanford working with Professor Brian Wandell and Joyce Farrell, and she's going to be talking about image system simulation for 360-degree camera rigs.
Okay, hi everyone. My name is Trisha, and I'm here today to talk about an image system simulation toolbox that I've been working on and how it can be applied to camera rigs that capture 360-degree content. So as you guys are probably aware, there are many different kinds of camera rigs that are available today. So I'd like to start off by just going through a couple of examples. So first here we have two rigs from Facebook. The one on the left has cameras arranged around a ring, and then the one on the right has cameras arranged in a ball all facing outward. Similarly, we have here the GoPro Odyssey, which is kind of like the Facebook rig with cameras in a ring, but there are 16 of them instead of 14. We have these more novel and unique designs like the Spin VR camera that Robert talked about earlier this session, or this stacked omnistereo representation, which Giant talked about in the previous presentation. And we have a bunch of these more commercial options, such as the Samsung Gear 360 on the left and then the GoPro Omni on the right. And these guys capture monoscopic panoramas, but they're more geared towards consumer product. So as you can see from this quick overview, there are many different kinds of rigs out there. But most importantly, each of these designs have their own unique number of cameras, their own unique arrangement of cameras, as well as differences between the camera hardware, such as the lenses or the sensors. So let's suppose you want to design your own camera rig. So how would you decide which type of configuration to go with? So due to the amount of variation in these configurations, prototyping a physical rig can be very difficult. So here I have an image from Brian Cabral, who is the director for the Surround 360 VR team at Facebook. And in this image, he demonstrates some of the various prototypes his team went through to get the Surround 360 camera. So here you can see a variety of different configurations, different testing setups. There's just a lot there. And all of this work eventually led to the final camera rig, which looks something like this. So Brian's example is evidence of the resource and time that's necessary in order to physically prototype one of these 360 rigs. So in this talk, I would like to introduce a simpler solution, and that's to use simulation. So here I'm going to talk about this MATLAB-based image system simulation toolbox that could potentially allow you to prototype and evaluate your rig completely in simulation. So here's an overview of what I'm going to talk about today. First, I'm going to go briefly through the camera rig pipeline in order to give you some context about where our simulation sits within this system. Next, I'm going to talk about the steps in our simulation in more detail and kind of show you how to use it. Then I'm going to show you some examples of simulated images from the rigs I showed you in the first slide. And lastly, I'm going to close on some of the open source tools that we have available. So one note is that all the 3D scene models that I've used in this presentation are from Benedict Bitterly, with some minor adjustments to make it work with our tools. And you can find all the original scene data on his website. So first, I want to give you some context about where the simulation sits. So the goal of these camera rigs is that given a scene, you want to be able to capture it and then have the user experience it through some sort of display, like a head-mounted display. So we start with a scene we want to capture, like the Grand Central Station here. And we have a camera rig that you've either built or you've bought, and you put it into the scene and you capture images, one set of images per frame. So you have one image from each of the cameras on the rig. You send those images to a stitching algorithm, which will put them together into a panorama, either a stereo one or a monoscopic one. And this panorama is stored as data and eventually given to the head-mounted display. So depending on where the person who has the display is standing or looking, you would render a new viewport depending on the panorama. So our simulation toolbox creates images from the first half of this pipeline. And the images we generate from this toolbox can be used to evaluate multiple steps further down the pipeline. So there are many uses to these simulated images. For example, you might be interested in how your choice of lens will affect the captured images that come out of your rig, or maybe how small, minor physical errors in your camera positions when you're building the rig will affect the final panorama. or maybe even how the final image you put on the display of the head-mounted display compares to the actual objects in the original scene. So in this way, simulation can be incredibly useful, and we can use simulation to evaluate and predict how different design choices you make in your rig can affect any of these outputs. So in the next few slides, I'm going to go through the various steps of our simulation in more detail. So our simulation toolbox is in MATLAB, so I've included under each image the associated MATLAB command that generates that image. And I hope these commands show you that we've tried to write the toolbox in a way where it's really easy to change different camera parameters or the rig configuration. So we start with a scene that we're interested in, for example, this living room scene shown here. And this scene contains information such as the geometry of the scene, different materials attached to the objects, the different image textures, and the lighting conditions within the room. And all of this is loaded into MATLAB using a read command. The scene format we deal with here is the PBRT format because PBRT is the ray tracer that we use in our simulation, and a little more on that later. So next, now that we've loaded our scene into the toolbox, we want to be able to place a camera in the scene. And so we do that with the standards graphics lookat command. So here I've placed the camera next to the sofa, kind of overlooking the scene. So for this example, I'm only doing a single camera, but you can imagine if we want to simulate the rig, we would just repeat the same steps at the different camera locations with the right camera parameters. But for now, this is just a single camera. So now that we have our camera placed in the scene, we want to choose a lens to attach to the camera. So our toolbox has a variety of different lenses, and many more can be added as long as you know certain information about the lens you want to use. So here we're going to use a wide-angle lens with a field of view of roughly 100 degrees. And on the right, you can see a schematic of this lens. And in this step, we can also set things like the aperture diameter or the focus distance of this specific camera. So once we've set the lens, we now want to use the ray tracer to essentially render the image through the camera. So the ray tracer will conceptually trace rays from the scene through the lens and onto the sensor. The ray tracer we use is a modified version of PBRT, physically based ray tracer. And I want to add that we've Dockerized the ray tracer, so in order to run this toolbox, you don't need to compile any of the code. You can just run it all in MATLAB. I also want to add that our simulation has realistic units. So for example, this sofa is 2 meters wide, and that lens is 10 millimeters wide. And also that our simulation, we ray trace spectrally, which means that we care about wavelength information. So for example, you might want to specify that the light coming out of that window in the back has a radiant spectrum that looks specifically like this. So we simply run this MATLAB command, and then we calculate the light that comes from the scene and arrives onto the sensor. So the light that arrives onto the sensor is called the sensor irradiance. Here I've represented that data as a RGB image, but it's actually a multispectral data, which means that each point has different values over wavelength. So for example, this specific point on this lamp has irradiance values from 400 to 700 nanometers, as shown in this plot here. With the rendering, we also get a depth map associated with each image, and that could be useful if you're someone who works on stitching and wants to use it as a ground truth or for reference later in your pipeline. So all the steps that I mentioned previous to this rendering step run pretty fast, so on the order of a few seconds. Ray tracing, though, is typically a slower process. So for this image, a 2048 by 2048 image with a certain quality level, on an 8-core machine takes around 1 to 2 hours. So that is pretty slow. However, to reduce this time, we've set up our toolbox in a way that lets you run all your rendering on Google Cloud if you have that set up. So with G-Cloud, you could run 16 of these images, so all the images from a single rig, in less than an hour. So you can consider that, like, if you were to run it sequentially, to be roughly 4 minutes per image. And so that's a lot faster and can reduce the computation time immensely. And to do that, you would simply change your render command to something like gcloud.render to specify that you want to render on the cloud. So now that we have the sensor irradiance, we want to compute the sensor output. So in this step, we're going to simulate the sensor, and we can do that by specifying various parameters, such as the color filters or the filter transmittance. here we're going to use just a standard Bayer pattern and a standard RGB filter. You can also specify different parameters, such as the pixel size or the sensor size, the exposure time, different types of noise properties. And the sensor and ISP simulations are all part of the ISET toolbox, which is one that we've also developed and attached to this toolbox. I'd like to also add that a lot of these parameters can be measured directly from a real physical camera. So if you have a camera on hand and the right equipment, you could simulate that camera specifically. So lastly, now that we have the sensor raw data, we're going to run it through an image processing pipeline in order to get our final RGB image. So this step includes things like demosaicing or illumination correction. And so here is the final RGB image of the living room generated through the entire simulation toolbox. So once again, to simulate a rig, you would just repeat these simulation steps for every single camera in the rig. And we've written the toolbox in a way that makes it very easy for you to iterate through different variations of the rig, such as changing the lenses or changing the number of cameras, or even changing the scene itself by removing or adding lights. And to show you how easy it is to simulate different configurations, in the next few slides, I'm going to show several examples of simulated images that match some of the rigs that I showed you in the first slide. So first off, I'm going to simulate the Facebook Surround 360 camera. So this rig contains 14 cameras with wide-angle lenses arranged in this ring. In addition, there are 3 cameras with fisheye lenses, 1 pointing up and 2 pointing down. So I've arranged my simulated cameras in this configuration and set all the parameters to try to match the specs given for this camera online, including the sensor parameters, the lens, and the geometry of the rig. And so here are the images that's generated from the simulation. Here we have the images from the adjacent cameras on the circumference, and here we have the images from the top and bottom fisheye lens. So the Facebook camera is unique in that the stitching algorithm associated with this rig is available open source. So what I did was I got the code down and I ran the simulated images from the previous slide through the stitching. And here we have the panorama generated with the Facebook code and the Facebook rig for the left eye and the right eye. So you can see that with simulation, you can do all these kinds of things without having to wait for the actual camera to be built. And you can imagine analyzing how your algorithm performs as you iterate through different designs in your rig. So next, I'm going to simulate the GoPro Odyssey. It's similar to the Facebook. Instead of 14 cameras, it has 16 around a slightly smaller circumference. Again, we simulate the lenses and sensors to best match the specs found online. And here we have the simulated images from a bedroom scene from the adjacent cameras on this rig. And now we're going to deviate from these rings of cameras and do 2 different rigs that generate monoscopic panoramas. First, here we have the Samsung Gear 360, which is 2 cameras with fisheye lenses placed back to back. And here we have a scene from a bathroom scene through this camera. And lastly, we have the GoPro Omni, which consists of 6 GoPro cameras arranged in a cube facing outward. And here are the simulated images from a living room scene. So I hope these series of examples have emphasized the flexibility we have with simulation. As long as we know certain information and the specs about this camera rig, we are able to generate simulated images from many types of configurations, from many types of cameras in many types of scenarios. So the toolbox I've been describing can be found on our GitHub page. We also have a wiki page that we're constantly updating with information on how to use the tools and how they work. The tools are MATLAB-based, as I mentioned before, and they primarily, what they do is they read in these PBRT scenes, and they let you easily add cameras, move them, modify them, and render images out through them. I want to emphasize that this is end-to-end simulation, so we're going from the scene through the lenses onto the sensor through the ISP, and finally resulting with the final RGB image. And finally, for those of you who say you work on stitching and you don't wish to simulate the camera rig design and hardware, I'm going to use the toolbox to put up a data set of simulated images from 6 different scenes. And this data will include RGB images captured at the end of our simulation, along with depth maps associated with each image. And these images are simulated through the Facebook Surround 360 camera, again with lenses and sensors that roughly approximate the specs. I'll also include the rig geometry information, along with various camera parameters that can be useful for calibration. So I started off this talk talking about why I felt simulation was useful in this context. So simulation can make camera rig prototyping faster and cheaper, and you can evaluate algorithms without having to physically build a rig. Then I talked about the simulation toolbox that you can apply to simulate camera rigs, and I showed a variety of different example simulations of a few camera rigs we have available these days. And all our code is available on our GitHub page, so please check it out if you're interested. Thank you for your time.